Yeah.
So for this final example in the improper integral section, I wanted to go and start building up some ideas that we're going to use in series and sequences in Chapter 9. So we're going to look at a more general type of integral problem here. So this is more general because why?
Have another variable in it?
We have like another variable in it. Exactly. What's that variable? P. Okay. So we're going to kind of consider all the various cases of integrating from 1 to infinity, which is obviously an improper integral, of the quantity 1 over x to any power. Does that make sense? This is going to be a very common thing that comes up in series, or it's going to be related to the what's called the harmonic series, the most basic and famously divergent series that there is. But also it's going to relate to all these other series that are named what kind of series? It's right there, John, if you want to grab it. P series, yeah. These are called P series. P series are some of the most basic, easy to work with series, but they kind of relate to going back to this problem. They're very closely related to this. So that's why I'm making a big deal about it. Okay. So we're going to have to break this down in cases because P could be anything, right? So I said first let's just take a very specific thing and look at P equals 1. This eventually will become the harmonic series that we look at and use all the time. So what if P is just 1? So then it's just 1 over x. So why am I writing this limit out here again? Because it goes to infinity, right? We've been doing that a whole bunch. So that should be obvious. We know the integral of 1 over x is ln of natural log of the absolute value of x. We don't really need to worry about the absolute value because these are both positive, right? So then we stick them in with the fundamental theorem. And can you guys help me finish this guy off? So this is going to be the ln of infinity as b approaches infinity minus 0. That has no b in it, the limit doesn't affect it, and the natural log of 1 is 0. So what does this become? Infinity. So this problem, the area under 1 over x when p is 1, diverges when p is 1. So that's a divergent integral. One you want to remember. So it's going to come back again and again. Okay, so what about if p is not equal to 1? So if p is not equal to 1, you can't just like get rid of the p, right? So I just left it as p and thought of it as a constant, a solid number. So I'm not thinking of it as a variable even though it's varying. I'm just thinking about it as a constant. And then I'm going to break it down into 2 cases down here. Okay? So if it's a constant, can't you just integrate it like that?
Yes.
Power rule, straight up, that's it. Got your limits of integration there, okay. This I rewrote. You guys see how I rewrote it? You can turn that around. That's 1 minus p. That is this. That might be a little sneakier. Why is that, the x quantity, that? Might need a little scratch work, right? So why does this become this? It's because that's equal to x to the 1 minus p, right? But now it's on the bottom. How did I get from here to here?
The negative.
I pulled out a negative. So I didn't even really think about doing this first. Instead, I just pulled out a negative to begin with, and I said, well, if I pull out a negative, then I get p minus 1. And that negative puts it on the bottom, right? Okay. So now we've got that. We've just got to stick those numbers in. So I stuck those in. I put b in for x. And I put 1 in for x. Why did that just get rid of everything else? Well, because 1 to any power is 1 unless that power happens to be infinity, but we're not going to think about numbers that large in this case. So that's just 1. We good so far? Okay, then I just pulled this out because does it depend on b? No, so I can pull it outside of the b-based limit. Okay, so now I have this guy. So now I said, well, I think this is going to go to different things depending on whether p is more than the 1 that we had over here that diverged, or if p is less than the 1 over there that diverged, okay? Because if p is more than 1, like 1.1 or 2 or 3 or 4, this is going to be infinity to some positive power, right? So what's that going to be? It's going to be 1 over infinity to something, so it's going to be 0, right? So if p is greater than 1, you're just going to have this thing out in front, times 0 times -1. Yeah? So that's really going to change around. How could I reduce that? Because there's a traditional way to write this. Yes, thank you, Kylie. There you go. So not only does it converge, but we just figured out if p is bigger than 1, regardless of what p is, we just came up with a whole family of convergent solutions. You don't anymore have to do this problem separately for each and individual value of p. Now we know if p is 2, does it converge or diverge? Converges. What's it converge to? 1 over 2 minus 1. If p was 3 up there, then you just figured out it converges. It converges to 1 over 3 minus 1. If p is 4 over there, it converges to 1 over 4 minus 1. Do you guys get it? Now, what happens if p is less than 1? Well, we got to separate that as a separate case. So I'm going to erase this. This is a big result, though, that you're going to want to get down in your notes later. Okay? So that's that one. So what if p, I guess I'll write that over here. What did it converge to? So we're going to say it converges 2, so it converges, and what does it even converge to? That's crazy. In mathematics, it's going to be kind of tough sometimes to see what something converges to. So not always you can have it come out so easy. It was p minus 1, though, right? That's its convergent value. Nice and simple. So what if p is less than 1? Well, if it equals 1, then we got to go and do that problem over there. What if it's less than 1? Then you're going to have something like 1 over b to, like, let's pretend it's like 0. Then we'd have b to the -1, wouldn't we?
Yeah.
So what would that do?
You take that in.
That'd go up to the top, and then we'd have this limit out in front, and the limit as b approaches infinity of b is obviously infinity. And if this was -2, wouldn't it do that and go to infinity even faster? If it was -3, it'd go to infinity even faster. So all these cases are going to have this thing out in front, 1 minus 1 over something concrete and constant, times infinity minus 1. So infinity times constant is infinity minus 1, infinity. So if p is less than 1, it diverges. So this guy's going to be divergent. Just like equals 1 is divergent. So we just discovered that for this integral over here, this guy is convergent if p is strictly greater than 1, and it converges to that. And we discovered that if it's divergent, I should say, if p is less than or equal to 1. That's a pretty big result in mathematics, not for just what we're working on now, but for some other stuff as well. What we're going to use it for is to work with an infinite surface, like what we have here in our book called Gabriel's Horn. More famous one's called Torricelli's Drum. So I'm going to just do the one from our book, I decided. So we're going to look at Gabriel's Horn. Gabriel's Horn is just taken by looking at the function 1 over x. Surprise, surprise, it's going to involve this thing, right? 1 over x, and we're going to look from 1 to infinity at the surface created by that and at the volume created by that. So let's look at the volume first. So 1 over x, can you guys see the 1 over x shape? So there's the surface. If I fill it in, I've got the volume. So let's find the volume first. The volume of this guy is going to be what? Can you guys help me out?
1 to infinity.
1 to infinity. Pi. R squared. Are we going to have washers here or discs? It's just discs, right? Just 1 over x
Squared.
1 over x squared dx. There you go. So it's a nice simple volume problem. The only problem is that it's an infinite volume problem. We couldn't have handled that before, but I think it's pretty easy once we've got this little theorem that we just came up with over there. So this is going to be 1 over x squared then, right? So you guys tell me, does it diverge or does it converge? Converges. Crazily enough, if you filled this thing up with an infinite amount of water, would you actually really need an infinite amount of water? If you started filling this guy up and it actually went all the way down to infinity, you'd have a finite amount of water. It converges down to a finite volume. because P is 2. And we could, of course, do this problem all over again. That would be doing it all over again. We've just got the answer up there. What's it converge down to? Well, pi is outside, right? So pi times 1 over 2 minus 1, which is pi times
So you need pi
1, which is pi.
You need pi.
That's actually also a definition of pi, is the amount of volume in this Gabriel's horn from 1 to infinity. Crazy, huh?
You just need pi 1.
Okay, so does that mean that the surface area is necessarily going to be finite or infinite? You might guess intuition, human intuition, based on what you've seen before, since you don't have a ton of calculus intuition yet. You'd probably think, well, if that turns out to be finite, then of course the surface area on that trumpet is finite. Let's find out.
We talked about this already.
So surface area is just the area on the outside. How could we do that? Surface area, we didn't do as much of that, but we'd go, 1 to infinity. And surface area, didn't we take like the arc length, which is like this piece? Well, that would be what? Square root of 1 plus dy dx here is
1 over x squared.
that, right? That's dy dx. So if you square that, you're going to get 1 over x to the 4th gx. That's just the arc length from 1 to infinity. Then we need to take that arc length, and if we want the area on the outside of this horn, we're going to have to multiply by 2 pi r, right? So 2 pi we can pull out in front, and r, well, think about the r of any one of these disks. It's just 1 over x. Okay, so that's going to be 2 pi. These are all x stuff, so we can't do it. So we could actually try to do this problem. We'd have to make a common denominator and all that stuff and see what happens. But see, we're getting into some more series type stuff here. I think you can do what's called a comparison. We're going to come back to this section once we start series and do some comparisons with improper integrals as well. I'm going to do that later. But you can actually do a comparison, because all the stuff in here, no matter what you make x, since this is 4th power, right, and that's the only x in there, this is really kind of just, you can just compare it to this problem. That part right here, that square root thing, you could of course try to do this problem. I think it's a pretty tough integral to do. But that part, no matter what you make x, is just going to be bigger than whatever this was, isn't it? Aren't you going to be multiplying this integral, this thing times something more? You guys get what I mean? And this one, we know what happens to this one right here, just this one. If I put a dx right there and stopped it. That one diverges or converges? That's the famously divergent one. So since that diverges and you're just multiplying more stuff by it, it should make sense to you that if it's already going to infinity and then you multiply it by more stuff, it's going to go to infinity. So this is going to be 2 pi basically times infinity. This is what's called a basic comparison test. We're going to get into that a lot more. So this is your first example of one. So this surface area of this infinite surface, Gabriel's horn, actually diverges, even though its volume converges. Infinite surfaces and volume